basically, if you'll notice, they're talking about the slope. That's why they use this m, the slope of the secant line. And they're just trying to emphasize that this is merely the slope of this blue line. So let's investigate what that is, because slope, as we know it, is y2 minus y1 over x2 minus x1, or the difference in the y's over the difference in the x's. So if I let this point be x2 and I let this point be x1, that would mean that this height up here is y2 and this height would be y1, because it's the association. I'm calling this point 1, and here's the x value associated with that and the y value associated, and I'm calling this point 2 and the x and y values associated with that. So what this x plus h means is it's just x plus some amount, call it h. So if this is x plus h, then the y value associated with that would just mean just plug in whatever that number is to your function, and that's why they called it this x plus h. And then you might be wondering, well, why is it just h on the bottom? That's because if I were to work out the algebra of it, I would have x2 is x plus h. That's x2. And then x1 is just a plain old x. So if I were to add these, I would just get, oh, these two x's cancel, leaving me with just h. And that's why there's just an h on the bottom instead of this difference. Likewise, on this other form of the difference quotient, and that's all it is just another form. If this is 0.1 and this is 0.2, they let 0.1 be equal to the x value. We're just going to call it a, so that y value associated with it is f of a. If I let this be 0.2, here's my x value associated with it, which is just, they call x, y2, which would be this f of x, minus y1, that would be this f of a, over x2, and in this case ours is called x, minus x1, and in our case it's called a. The next thing we're going to do is look at how to actually use this with a problem. So they've asked me, and this is what you're going to be required to do on both homework and on your tests. You will definitely have one of these questions at least on your test. At least one is what I mean. So be sure that you can work these. I'm going to find basically a formula for any secant line. So I could choose, let's say, this to be a secant line, these 2 points, and I'm going to get a formula that will give me that slope for no matter which two secant lines, which 2 points that I choose to make a secant line. So let's get that. I'll start down here. M of the secant line. This is going to probably be messy. And I need f of x plus h minus f of x all over that h. So the first thing I probably want to do is go and figure out what this mess is. And I've done pieces and parts of that in the previous section. So let's do f of x plus h, and all that means to do is take my f of x, and wherever there's an x, put in an x plus h. So this was how we worked it in the previous video, if you'll recall. And then it's just a matter of messy algebra. So it's 3 times, I'm going to multiply this x plus h times x plus h, that's x squared plus 2xh plus h squared minus x minus h. Then multiplying the 3, distributing it all the way through, I will get 3x squared plus 6xh plus 3h squared minus x minus h equals, let's see, what can I, oh, nothing simplifies in that, so I think that basically is done as far as what I get for f of x plus h. So let's play here. I'm going to write down f of x plus h, and it's this big wad of stuff. This is f of x plus h. So I would get 3x squared plus 6xh plus 3h squared minus x minus h minus whatever f of x is. And that's what this part tells me to do right here. And f of x was 3x squared minus x. And all of this was to be over h. I'm going to distribute the negative here. 3x squared plus, and this is just so messy. Alright, save you a few seconds there. Canceling out that guy, I've got a plus 1 and a minus 1. I've got a minus x here and a plus x. They cancel, leaving me with 6xh plus 3h squared minus h, and that's it, all over h. And this is going to equal, see how I see that there's an h in everything, so I'm going to pull it. 6x, oops, pulling that h plus 3h minus 1 all over h. Those two h's will then cancel nicely, ka-tunk, ka-tunk, leaving me with 6x plus 3h minus 1. And that is it for that one. If you notice in the solution to your what the textbook has, they do have an error in that one. Sorry about that, but this is the correct answer. And this is just a formula that will give me the slope if I pick any 2 points. I would pick an x value and some sort of h, and that would give me the slope at any point, any 2 points that I pick. So let's do the b part of this one. Do it in different color, just kind of to separate it. And m of the secant line here, I didn't graph this one, but you can if you would like. And I'm going to do f of x minus f of a all over x minus a. F of x happens to be x cubed minus f of a, I just plug in an a for my x, so that would be a cubed all over x minus a. And this looks pretty good, except for that I kind of know that that is the difference of cubics, and I'm sure you do too. And if you'll recall your formula, if you can't, look it up, just look up difference of cubics. And if not, we can discuss it in Blackboard Collaborate. But there are formulas for this. We can discuss how that's derived at some other point. Chunk, chunk. And my answer for this one would be x squared plus ax plus a squared. And there would be the formula for the slope of the secant line at any 2 points that you pick along this curve. This next problem is a word problem involving a secant line, and they have told me that the sound intensity I, and it is a function of r, and r happens to be however many meters that you're away from that sound source, is equal to the power, or the acoustic power, divided by 4 pi r squared. and they would like for you to give the slope of the secant line from points 10 meters and 15 meters. So in order to find the slope, I would need to get the two y values and the two x values. Of course, I know the two x values. This would be x2 and this would be x1. Of course, it doesn't matter, but that's what I'm going to pick. And then this is just telling you to get y2 and y1. And you are going to find the slope. All right. They also told me that P is 100, so I can go ahead and plug that value in, because for the problem that I'm doing, I'm using a power of 100 watts. I'll put my units in at the end just to make it not quite as messy. So I'm going to do I of R1, and R1 happens to be 10. So it would be 100 divided by 4 times pi times 10 squared. And this would yield 1 over 4 pi. Looking at units, that would be watts over, and my meters were squared here, so meters squared. I'll play this game again. I of 15, and this is going to be my y1 value, and this will be my y2 value. 4 pi times 15 quantity squared, and this would be 1 over, and by the time you reduce it and do your algebra, 1 over 9 pi watts per meter squared. So I would like now the slope of this secant line, so I'm going to do slope of this secant line, and I will take the two y values, subtract them, this being y2, this being y1, this being x1, this being x2, and I'll manipulate them from here. So y2, that's 1 over 9 pi minus 1 over 4 pi, and the x values are 15 minus 10, and in order to get this, I'm going to have to get a common denominator. I like 36 pi, so I'm going to multiply top and bottom here by 4, multiply top and bottom here by 9, so I'll have 36 pi on the bottom. If you need me to work that through at some point, just I can do that during a collaborate, and this would be, I believe, oops, I'd have a 4. Let me get that. I don't want to scratch it out. So I would have a 4, because I multiply top and bottom by 4 there, minus 9 all over 5. Then I would have negative 5 over 36 pi. This is divided by 5, so that's the same thing as multiplied by 1 over 5. This gives me negative 1 over 36, and seeing as this unit, let's put it in a different color, put it in purple. This unit was watts over meters squared, and this one was meters. My units here end up being watts per meters cubed. And once again, it seems that they have a bit of an error in their solution on their in their chapter review. They didn't, and it's just in the units, but they said that the secant would be watts over meters squared, and of course it wouldn't be. If you'll notice here, right there, that's an error, but not a significant one, but still one that somebody should have caught by this point. All right, irregardless, let's do the B part where they're wanting me to get the general formula as in we did the previous example. So it's supposed to be a general formula, so if you'll notice what I'm supposed to do is plug in an R2 for my R value to get my Y point, or my Y value point, and then same here for my point 1. So I'm going to do that. M of the secant line is, it's going to be Y2, and that just means plug in an R2, and I believe this is for any power, so it would be P over 4 pi R2 squared, this is going to be really pretty, minus P over 4 pi R1 quantity squared, because this would be Y2, this would be Y1, so it's Y2 minus Y1 over X2 minus X1, and this part is R2 minus R1. Not quite so bad there. Alright, I've got to make this a little prettier because it is ugly, so what I'm going to do is say, well, if I notice I need to get a common denominator, but all this junk is all the same, so I'm going to leave that as is so that I just have to mess around with 1 over R2 squared and 1 over R1 squared. And then I'll get a common denominator, and it's still all over all of this mess. I'll get a common denominator and then simplify, so that's what I'm going to do. Alright, really getting messy here. I'm going to take this and flip it so that I don't have this huge complex fraction. So I'll have R, and this guy right here will factor, so I'm going to go ahead and do that. Oops, it's supposed to be R1, R2, R1 plus R2 over R2 squared, R1 squared, and I'm going to say times 1 over, and then that'll be R2 minus R1. Pretty close as far as something that could cancel. If you'll notice, these two differ by a -1, so I'll do a little quick -1 trick and cancel those. Chink, chink, because they were just off by the -1, and I believe I have my final answer. And I guess if I was going to do a whole bunch of these, this thing was worth it, but I kind of found it easier to get the slope for the A part because it was numbers and it was things collapse a lot better. But what it is that I have now is, if I were to plug in a 15 for R2 and a 10 for R1, I would get -1 over 36. So let's say you don't believe me. Let's just check it out. M of the secant line, and I'm going to do this for R2 equal to 15 and R1 equal to 10, and I believe the power was 100. So let's just check it out real quick. So that's -100 over 10 plus 15 all over 4 pi, and then I've got 15 squared over 10 squared, and I'm going to do a little canceling here, make my life easier. You're gone, little buddy. Let's see, that's a 25, so I've got -25 over 4 pi, and that's a 15 squared, so I'm going to look at that as times 3 times 3 times 5 times 5, because that's 15 squares. That way I can do my canceling without having to multiply out the numbers, and I get equals negative 1 over 9 times 4 is 36 pi. Voila! Wasn't that a cool trick? That and this are the same, meaning that I got the general formula for the slope of the secant line of any 2 points on that curve. Cool stuff. Alright, I know you're still reeling from that last example because it was pretty exciting, but we're on to symmetry now. If something is symmetric about the x-axis, what it means, and I'm looking at this graph first, it means it's reflected about the x. So if I were to, here's the x-axis, I put a mirror here, I can see that it's the same on either side. Notice that it's not a function because it doesn't pass a vertical line test. So if it's symmetric about that x, yikes, it is not a function. Let's look at symmetric about the y-axis. Sometimes these are called even functions, and we'll discuss that in the next little part. But if I were to put a mirror here, I would see that it is reflected on either side of that y-axis. Cool stuff. We'll discuss what this means in our next little portion. If it is symmetric about the origin, what it means is it's a reflection about the x and the y. I call it a flip-flop, meaning that it is you reflect it about, let's just look at this portion here, and if I were to reflect it about the x-axis, I'm not really good at this, and then flop it across this y-axis, meaning a flip-flop, so flop it back across, then it is symmetric about the origin. We also call this an odd function. So let's look and see how we use this. It's just a way to describe it. They have 3 graphs here for me to look at. The first one being an even function, and they want you to note that it is symmetric about the y. If it's an even function and symmetric about the y, it has the property that if I insert a negative x for x, I'll get that function back. Now, just a visual inspection does not guarantee that it's an even function because it could be a little off. So I don't know for sure that it's even. I got a good idea that it's an even function because it looks like it is, but I can't prove that it is by visual inspection, but I can prove that it is in the following manner. I'm going to take this function that they've given me for a, and I'm going to insert a negative x. So that would be a negative x raised to the 4th minus 2 times that negative x quantity squared minus 20. And then I'm going to simplify this a bit, and negative x raised to the 4th is the same as x to the 4th. Minus 2 times negative x raised to the 2nd is the same as x to the 2nd minus 20. And if you'll notice, this equals f of x. This proves that this first function is even. Our second function, by visual inspection, I can say has no symmetry because it is not a reflection about the y, it is not a reflection about the x, and it is not a flip-flop, so we'll let that one go. Our c looks to be an odd function because if you were to flip it across the x, so just imagine flipping it, reflecting it about this x so that this guy would be up here and this guy would be down here, and then flopping it across the y, I see that it's possible that this is an odd function. How will I know for sure? I prove this condition right there. If I insert a negative x, I'll get the exact function back but negative. So let's try that for our c. H of negative x equals 1 over negative x quantity to the cube minus a negative x. And for this one, I note that negative x times negative x times negative x is the same as negative x cubed, and this is a plus x. Notice that these two are exactly the same except for a negative. So if I were to, say, multiply top and bottom by a negative, then I would get, which is negative h of x, which now proves that this one is indeed odd. Even. And that concludes section 1.